Hi, my name is Jeff Bowles. I work on the Vulkan driver and compiler at NVIDIA. And today I'll be talking about doing machine learning in Vulkan using Cooperative Matrix 2. That does not work. Okay, so I'll give some background and show what Cooperative Matrix 1 supports and what its limitations are. And then I'll use llama.cpp to motivate the new features that are in Cooperative Matrix 2 and show some perf results for that. And this Vulkan loving cat was generated using stable diffusion.cpp, entirely using Vulkan, using Cooperative Matrix 2, and with competitive performance to the CUDA backend. Okay, so the goal is to accelerate machine learning, and one of the critical, most expensive operations is large matrix multiplies. And normal scalar math isn't really well suited for this. Anything you do would need to be tuned for some specific hardware, and it doesn't offer a way to take advantage of dedicated matrix hardware like Tensor cores. So the Cooperative Matrix extensions introduce new group-wide matrix types and matrix multiply instructions on those types that can map to hardware like the Tensor cores. So these are medium-sized matrices, and the values are spread across a group of invocations in a way that's opaque to the developer. And all the invocations in that group cooperate to actually perform the multiply. And so this is a primitive that shaders can build larger, like general matrix multiply kernels out of. So some quick terminology. Cooperative matrix, it's what I just said on the previous slide. There was the KHR Cooperative Matrix extension, which I'll call CoopMat 1. And this was released in about June of 2023. And it's pretty widely supported today by many vendors. And it supports subgroup scope matrices. Then there's the NV Cooperative Matrix 2 extension, which I'm calling CoopMat 2, which was released in October 2024 and is currently only supported on NVIDIA. And when we talk about matrix multiplies, the terminology is to say D equals A times B plus C, where A is an M by K matrix, B is a K by N matrix, and C and D are M by N matrices. The matrix types in the shader are templated by component type, scope, rows and columns, and use, where use is either A, B, or accumulator. And FP16 and Int8 data types are pretty broadly supported, hopefully more in the future. I think Ralph may have mentioned one in his slides yesterday. So if you wanted to write a matrix multiply shader using Cooperative Matrix 1 the natural way, this is what it would look like. Each work group computes one tile of the result by doing a sum of the product of a row of A and a column of B. And so this code's it's short, it's easy to write, easy to read, but the performance is disappointing. If you do this, I got about 8 teraflops on RTX 4070 out of a theoretical peak of 116. So that's a sad face. And the problem is really that the tiles are too small. The data ends up getting fetched repeatedly. There's not enough reuse, and so it ends up being memory bandwidth limited. So now if you want to fix this, you need to get as much reuse out of the loads as you can. And so that means kind of loading slivers of A and B and maximizing the size of the result so that for each value you load in A and B, you can do as many multiplies as possible, multiply as many combinations as possible. And to really maximize the size of the accumulator, you end up saying like, okay, a single subgroup wasn't enough. I need a whole work group. And so this figure kind of shows like, okay, let's take 8 subgroups, arrange them in a rectangle. So the accumulator is split across all 8 subgroups. For A and B, there's some sharing of tiles. And the numbers here indicate which subgroups need which tile. And then to further optimize the loads, since there's this redundancy, you actually want to like split that up amongst those subgroups, copy it into shared memory, and then have the redundant loads happen out of shared memory. And then additionally, you can kind of see in the code that it's actually pipelined one step. So like it's loading for the next iteration while it's computing for the current iteration. So this all works. The performance is pretty good, 98 out of 116. That's really good for it's really hard to hit peak rate for the tensor cores because they're so fast. So you can do this. The code's on GitHub. You're welcome to take a look at it. But I showed this as pseudocode, and I've highlighted these couple of red lines. They don't show up very well. I've highlighted these red lines. There's a lot of details hidden in those lines. You can see it on GitHub, but this was tricky to write. It's too I mean, really, it comes down to it's too complex. It's far from being the natural code that you would want to write, and so that kind of suggests that this is the wrong level of abstraction for what we're doing here. Okay, so the problems we've identified are there's a lot of tiling, right? There's a work group tiled into this two-dimensional arrangement of subgroups. Each of those has a two-dimensional array of matrices. It's a lot of tracking and bit twiddling, and the compiler could just do this. Like, you shouldn't have to do this in the shader. Similarly, when doing these copies through shared memory, you need to split the A and B matrices, split it amongst all the threads. You need to use the most efficient memory access pattern, use the most efficient load size. It ends up being a lot of complexity. And again, the compiler can just do it for you. Like, the compiler is just great at doing that kind of thing. This example I showed, it didn't include bounce checking. So even, I said it was too complex already. It didn't have bounce checking. In the real world, like the tensor size in memory is not always a multiple of your tile size. And so you do have to have bounce checking along the edges. And if you think about even something that should be really simple, like I just want to store my result matrix out to memory. The built-in function for store is it doesn't do the bounce checking. So what's the fallback then? Well, you don't know which values belong to which row and which column because it's opaque. And so the only way you can store it out is to first copy it to shared memory, where you have it now in a linear arrangement and you know what needs to go where. The problem is we made this tile so big it doesn't fit in shared memory now. So now you need to do a workaround for that. So it's like workarounds on top of workarounds just to do something that should have just been store, right? Additionally, there's a few operations that are missing. Being able to convert accumulators back to A matrices so you can then do some more operations on it, doing row or column reductions. So those are missing as well from CoopMat 1. But the big takeaway really is, it doesn't have to be so complex. The compiler could have more of the responsibilities, and it could be a joy to use. And if you look around at the ecosystem, this is kind of the direction things are going. This example is from Triton. So Triton is a Python-based language / compiler for machine learning. It's from OpenAI. And even if you don't know Triton, you look, if you can read the example code from the back, you can kind of tell that it's similar to the simple example I showed at first, right? Like, it's iterating over the k dimension, loading a slice of A and a slice of B, and doing the multiply and accumulate. And this table at the bottom is their table. It's from their webpage, and it's comparing what the Triton compiler does to what CUDA does. And so the Triton compiler handles the staging through shared memory. It handles decomposing work groups into subgroups and tiles. And Cooperative Matrix 2 is intended to, it's targeting the same things. So now this is the example rewritten to use Cooperative Matrix 2. So CoopMat 2 has 7 new features, and this is using 3 of them. It's using flexible dimensions, work group scope matrices, and tensor addressing. So at the top of the slide, you can see the matrices are work group scope now and using a much larger tile size. And so the flexible dimensions feature means that the driver advertises a granularity for the matrix, and any multiple of that granularity you can use. And the compiler just breaks it down into the hardware granularity for you. The compiler also splits up work group scope into subgroup scope if it needs to. And this isn't really an explicit feature, but the intent is that if you're using work group scope, the compiler can also copy through shared memory for you. So all these optimizations we had to do before, and now it's just all built into the compiler. So we're basically back to the code looks like the simple example, but the performance is still good, 97. So happy face. And so the other feature you can see being used here is the tensor addressing. So I'll go into detail in the next few slides, but you can see it's creating the tensor layout objects it's filling out their dimensions, and then it's doing a slicing operation, which is selecting a subrectangle in memory that it's going to load. And this replaces all of the addressing math that was in the previous examples. Okay, so the tensor layout is a software structure that gets constructed in the shader, and it's meant to be an extensible way to pass parameters that are related to addressing calculations. So the layout describes the shape of the tensor in memory. So it's not about the matrix that you're loading into, it's the shape of the tensor that's in memory. The layouts can be up to 5-dimensional. Each dimension has size, stride, offset, and span, and these define the shape of the whole tensor itself, as well as this little slice that's being loaded from. And this layout logically maps matrix row and column numbers to a 1-dimensional index, and that 1D index is converted to an n-dimensional coordinate in the slice, and then just add the offsets, multiply by the strides, and that's how the compiler generates the final address. Okay, so what's the point of this? Why have this object at all? So these tensors and slices, they have the nice property that all of the access, all the memory loads and stores are going to go through the slice. And so when the compiler is doing something like needs to copy through shared memory, it doesn't have to worry about like, are you row, major, column? You know, it doesn't care. It just says like, okay, there's the slice. I need to get that from global memory into shared memory, whatever the most efficient way possible is. And more generally, these layouts are amenable to compiler optimization and potentially hardware acceleration in the future. If there's some dedicated tensor core thing that we want to use, this is a nice way to kind of build a descriptor for that. So what I showed in the previous slide is like the general case of how the addressing calculations kind of work. But there are lots of optimizations the compiler can do. And the obvious one is if the shape of the slice is exactly the same as the shape of the matrix, then it doesn't have to do those calculations. Just row and column coordinates are your slice coordinates, and it's free then. So in the common cases, it's just as cheap as the old row and column major addressing was. During development, I had considered having an address calculation callback, so like fully programmable addressing, but it wasn't practical to optimize it, and like the compiler couldn't figure out your intent. It couldn't really tell what part of memory you were accessing, so it didn't work out. And so this is kind of a sweet spot. It's these tensor layouts and views, which I'll show in a few slides. They handle the common cases, but they do it in a way that's friendly to the compiler. The compiler is able to optimize. And so I think it's worked out well. So this is the spec's logical description of the tensor layout state and the addressing calculations. I'm not going to go into detail, but the spec is really clear and precise about how the addresses are calculated. And it looks expensive in its full generality, but like I said, in practice, the common cases are still really efficient. Okay, so the tensor view is an additional optional object used to describe more complex addressing calculations. And it allows changing the number of dimensions and permuting the coordinates. And this is most commonly used, like the most common use case for this is transposing your matrix, which is just permuting the 0 and 1 coordinate. But this is meant to be more general. It handles some of these reshaping operations that show up in other machine learning APIs. And I'm not going to go into a lot of detail on this one. Again, this is kind of how the spec describes it for reference, but I'm not going to dig into the details due to time. Okay, so moving on to real world use cases. So I wanted to find an open source library that I could add Cooperative Matrix to support into, to prove it out really and make sure it was handling everything it needed to. I chose llama.cpp because it already had a nice Vulkan backend. It's really well written. I've enjoyed working in it. It's very easy to build, unlike some of these Python-based frameworks. So yeah, it's nice. Everybody should try it. So this figure on the right kind of shows the architecture of the llama CPP code. So there's kind of the core of it is there's this GGML API. This is the tensor library. And then llama.cpp is an LLM project coded against that. Whisper is audio to text. Stable Diffusion is text to image. And so they all code against this GGML API. And then there's a bunch of backends. There's CPU. There's actually several flavors of the CPU backend optimized for all the different vector instruction sets. There's CUDA and ROCm and Vulkan and SYCL and Metal and Musa, and like I'm sure I'm forgetting some of them. There's a bunch, and there's a Vulkan backend, and it supports pretty much everything, and it's not everything. It supports everything for the common cases, and it's efficient and works well. And so GGML also has support for these quantization compression formats, which I'll talk about on the next slide. And so there end up being 4 main use cases to accelerate with Cooperative Matrix. There's a matrix-matrix multiply, a mixture of experts matrix-matrix multiply, flash attention, and these quantization formats. And as of today, the Vulkan backend is broadly supported across a bunch of hardware. The matrix multiplies have a scalar, CoopMat1 and CoopMat2 paths. Flash attention currently only has a CoopMat2 path, and the quantization formats are supported in all 3 of those paths. Okay, so these quantization formats, they're really compression formats, and there's really 2 reasons for this. The first is that these are big models. The model has to fit in VidMem. If it doesn't fit in VidMem, what's the point? It's going to be too slow. But then additionally, the matrix vector multiplies are bandwidth limited, and so the more compressed you are, the better your performance is. So it's good for that too. I'm showing one example format here. It's called IQ4NL, and so this has 32 elements per block. Each element is represented as a 4-bit index, and then there's a shared 16-bit scale, and it has a lookup table. And so to decode one element, you look up the 4-bit value, run it through the lookup table, and multiply by the scale. So it's pretty easy. These formats don't all have lookup tables. Several do, several don't. They're usually either 32 or 256 elements per block, usually around 2 to 8 bits per element, and they're stored in memory just as a array or tensor of blocks. And it reminded me a lot of the block compressed texture formats. It's kind of a similar way of storing things. Now, if you focus on the dequantization logic for this specific format, they all kind of follow a pattern. So they need to compute the index of the element that's being loaded, and then from that index compute the block address and a coordinate within the block, and then actually do the dequantization logic, in this case, the lookup table and scale. And so, like I said, they all kind of do this. It's a pattern, and we can design an API around that pattern. So in our matrix load function, the compiler, you tell it the block size. That's part of the tensor layout state. And so then when it computes the element it wants to load, from that it computes which block it's in and your coordinates within the block and the coordinates of the block as well. And it calls a callback function that you provide in the shader. And so your shader, it takes a buffer reference parameter and these coordinates, and you implement the logic to do the dequantization. And then when you, so that's in a separate function, that's your callback function. And then when you actually want to load the tensor, you just pass in a quote unquote function pointer. And so this is a nice composable way to support dequantization, right? So like there's a single matrix multiply shader, there's a single flash attention shader, and then there's a set of these dequantization functions, and you just plug them together, compile all those combinations. So this worked out pretty well. My one regret about this is that many of these formats are amenable to decoding 2 or 4 neighboring elements at the same time. There's shared calculations they can do. So I kind of wish that I had made this callback support returning a vector, like a 2 or 4 component vector. So if we ever standardize this, make an ext or something, that's something I would want to add. In the meantime, there's a workaround where you can kind of write the function as if it's decoding 2 or 4 elements, and the compiler is going to invoke it for the neighboring elements. And if it can comment out, it's going to inline and comment out the code, and you get most of the benefit. So it's still pretty efficient. Okay, the mixture of experts shader, it's a twist on the normal matrix multiply, where the rows of the B matrix get permuted by looking up through a table in shared memory. The top block of code here shows the scalar and cooperative matrix 1 path. The middle code shows using another callback function to do this. So this is the callback function for a load. It does a little bounds check. It looks up to the shared memory table and fetches the right value. I wasn't aware of this use case when I initially added the callback functions for the quantization format, so it was nice that it worked out for both. So that was pretty satisfying. And then at the bottom, so when you have to store this matrix, when you store the accumulator matrix out, it also needs to remap through this lookup table. And so this uses a per element operations. There's this coopmat per element function. You again pass it a callback function, and this callback function does a bounds check, does the remap, and stores it out to memory. Okay, flash attention. So the last regime we need to support is flash attention. So attention, without the word flash, is a common operation used in transformer networks. And it's a function of three matrices, Q, K, and V. And you multiply Q by K transpose, scale it, apply the softmax function, and then multiply that by the V matrix. And softmax here, it's these exponentials, and it's basically normalizing where the denominator, it's normalizing rows of the matrix where the denominator is this sum of exponentials. So normally if you implement attention, it's two matrix multiplies and this softmax thing, and all these intermediate values need to be written out to memory. And so that's the big expense doing this, is all the bandwidth. Flash attention is a trick to fuse this all into one shader. And at first glance, it seems like you need to know that whole sum before you can actually compute the softmax. But the trick is to kind of observe that it's just a scale. And so while you're iterating, you compute what you know so far and use that as the denominator. And then on the next iteration, you have more information, you update what that should be, divide out the old scale, multiply in the new scale, and keep going. So it's a neat little trick. Seems like it would have floating point issues, but I've actually read it actually is better. It's more stable, so that's cool. Yeah. So this is a very popular optimization. The transformer networks are getting more popular, so this is an important use case. So this shader needs a few additional cooperative matrix 2 features. It needs row reductions for the softmax. It needs matrix use conversions. So the Q K transpose product is an accumulator and needs to get converted back to an A matrix. And it uses the per element operations again. So the reduce, it also uses a callback function. Any symmetric function will do. So this is showing a max. And then it also uses the per element callback to clear out some padding elements. It does a max reduction, which I didn't really talk about on the previous slide. But it does a max reduction, and when you get this first intermediate product, it's going to have zeros in the padding, and you don't want zeros in your max. You want negative infinities in your max, and so it uses this callback function to just fill the edges with negative infinities. Okay, so to summarize how each of these shaders is using CoopMat2, they all use workgroup scope, flexible dimensions, and the tensor addressing, and that keeps the shaders simple, and it's good for performance. Everything uses the block load feature for the quantization formats, and then the mixture of experts and flash attention use the other features. All right, so performance results. So this is from running Llama Bench across a variety of models. If you can read them, the names are at the bottom. This slide is showing prompt processing with 512 tokens. This is one of their standard benchmarks. And prompt processing is the operation that uses the matrix multiplies. This is the one that benefits from cooperative matrix. So for each model, there's 4 bars. The dark blue is Vulkan, Vulkan with no cooperative matrix. Orange is Vulkan with cooperative matrix 1. Green is Vulkan with cooperative matrix 2, and the light blue is CUDA. I'm including CUDA for comparison. So the high-level message is that the CoopMat2 path is competitive with CUDA. Both CoopMat1 and CoopMat2 are a big speed up from the scalar path. There's probably room to tune the CoopMat1 path to be closer to CoopMat2. I spent a lot of time tuning CoopMat2, but not really CoopMat1. And there's kind of an interesting thing with the comparison against CUDA. CUDA is, so the Vulkan shaders are all using FP16 for all of this. The CUDA shaders are using int8. Some of these quantization formats, the data is kind of in mostly int8 with floating point scale, and then they take the other matrix, convert it to a quantization format. And so they both have int8 stuff that they multiply and then scale whole tiles. So it's pretty different code. So it's not like quite an apples to apples comparison, but it ends up being kind of a pleasant surprise that, even though int8 has like double the peak speed, the FP16 Vulkan path is still keeping up. So this is, and that was on RTX 4070. This is also RTX 4070 doing token generation. So token generation does matrix vector multiplies, and that's not accelerated by Cooperative Matrix. But this is the other main mode of operation. When your LLM is actually like spitting out words, it's the token generation stuff. And I just wanted to show that the Vulkan backend is still competitive with CUDA. There's really two bottlenecks in this mode. There's the bandwidth for the matrix vector multiplies, and then there's several other like very small shaders that run. And it's just like the overhead of running the small shaders. CUDA is using the CUDA graphs feature, which is intended to optimize these small back-to-back dispatches. So it gets a boost from that. We're hoping to have some driver optimizations to kind of catch up a bit there. So I'm hoping this improves in the next major release. This is prompt processing on an RTX 6000 ADA, which is a nearly perfect maximum number of SMs ADA chip. But it has a very low power limit. It's like a 300 watt GPU. So it has a pretty different, it has a pretty different like compute to memory bandwidth ratio. I'm not actually sure if it's more bandwidth limited or less. I want to say it's less bandwidth limited. But it's a different mixture, and so the performance ends up a bit different. And Vulkan is probably, the CubeMat 2 path here is probably edging out CUDA at prompt processing. And then again, token generation, CUDA is still winning, probably because of the small dispatches. There's one other trend I wanted to mention in this slide that you might notice, which is you can see the CubeMat 2 is often slower than CubeMat 1. And if you're wondering why that is, it's because all the CubeMat 2 numbers were run with flash attention enabled. And for these small token generation benchmarks, flash attention doesn't really help, and sometimes it hurts a bit. So it's not anything inherently wrong in the CubeMat 2 path. I don't even know if those shaders are running in this token generation benchmark. It's just flash attention on versus off. Okay, so to summarize, machine learning acceleration is possible in Vulkan today using llama.cpp with Cooperative Matrix 1 or 2. The CubeMat 2 extension is available now. The specs and tooling have all been published, and they're in the latest 304 SDK. It's currently supported in NVIDIA's developer drivers, and it'll be in the next major release, R575. And it's supported on all NVIDIA RTX GPUs, which is touring through Blackwell. So try it yourself. Llama.cpp is really easy to build and use. Give it a shot. Thank you.
So I'm sure that some developers are wondering, when is this going to be available more broadly across the Vulkan ecosystem? Can you speak to that?
I cannot say anything about other hardware vendors' plans. I will say that, there is a Vulkan MLTSG, and we talk about things like this, right?
Assuming
we're actively trying to do things.
The new extension does require hardware changes. You can't just do it in the driver.
No, it can really be entirely
Okay.
compiler side.
Cool.
Yeah, for us, it's no hardware change. We support it back to Turing. It's just compiler stuff.
You mentioned, I think there is a metal backend.
Mm-hmm.
Do you have any numbers of performance comparing to Vulkan?
I don't have any handy, but if you're curious, if you go to the Llama CPP repo, there's GitHub discussions. There's a discussion thread dedicated to metal performance. There's one about Vulkan performance. And in the Vulkan one, I even recently saw somebody had posted Molten VK versus Vulkan. And I think they also they were running on a Mac, and it was Molten VK versus metal. So there is at least one direct comparison data point there.
All right, so I have a question, which is, because I presume that this extension does exactly what a CUDA library does, or not?
I'm not sure what you mean, but it's kind of vague or broad.
Okay, so you say that Turing and onwards will support it.
Mm-hmm.
For you, it's doable just with compiler magic, no extra hardware instructions. and I see the spec is GLSL, but it suddenly has templates and function callbacks. So function pointers, and I'm just wondering what's the logic behind having that be a extra SPIR-V thing instead of like, let's say, a slang header library or HLSL or something like that.
Okay. So I mean the templated types have been in GLSL since the CoopMat 1 extension, and like the original CoopMat 1 was an NV extension in like 2019. I'm not sure what the state of Slang was at the time. We weren't really trying to do stuff in Slang then. I would love to see Slang support for Cooperative Matrix now. But you know, like we needed parameterized types, and it's template like syntax. It's not as fully featured as like C++ templates or Slang and generics. But it's just a way of expressing these types, and then in SPIR-V they're just normal type instructions. So I'm not sure if I've answered your question. Sort of. We can talk more after.
Just one last question over here.
Hi, yes or no? 2 questions. Can you
Yes.
implement a Gaussian blur in Cooperative Matrix 2? And 2, would it be performant, as in more than if you did a separable pass?
So like a convolution. Yeah. So there's no direct support for convolutions. I did at one point go through the exercise of trying to see, like, I wanted to make sure that, like, I wanted these tensor layouts and views to be expressive enough to do things like that. And so I did convince myself and wrote some pseudocode that you can do convolutions, you know, with padding, with the stride and dilation. Like, you can do all of those with the tensor views and layouts. I did not do performance tests. So I don't know if it's going to be especially efficient to do that. But yeah, I mean, you sort of can. I would, like, if I had all the time in the world, I would love to try out doing like a convolution extension, like some direct native support that the compiler can optimize, but I haven't had a chance to do that.
Okay, if we could just thank our speaker again.
Thank you.